and creating a ecosystem for rapid scaling it up. We talked about the electric vehicle policy requirement, the challenges faced for creating the right infrastructure in place, the range anxiety that the consumer is facing, and which is also hampering the faster adoption. And the EV safety issues were also touched upon today. The requirement of battery management system, the various battery chemistries that we are researching and we are likely to have, for scaling, increasing the scale up of batteries and EVs, and the various business models we talked about, which are available for available, and we are looking forward to the new business models that will be coming up. So, what about the impact on the grid? With so much of new demand challenges that we are facing, with the EVs getting connected to the grid and low voltage grid and demanding huge amount of electricity. So what is the impact that it's going to make on the grid, our electric grid? Increased load might put strain on the power systems. The integration of EVSE with the grid for smart charging is this is an emerging area that we need to work on and needs to be expedited. And ISGF has conducted a study of what kind of impact electric vehicle demand will put on the grid. And it is called EV Electric Vehicle Charging Infrastructure Planning Rollout for Bangalore City, which is also available for on our website and other places for you to view and go through. So the recommendations and the research results will be presented by my colleague Anand during the discussion. But before that, let me take the pleasure of inviting our moderator and the panelists for today. Unfortunately, Mr. Pillai couldn't be here today with us because of some family emergency. So Dr. Rahul Tongia has kindly accepted our request to be the moderator for this session also. So please put your hands together and welcome Dr. Tongia on stage for moderating the session A, technical session on electric charging impact on distribution grid, the challenges and the solutions. And he will be joined by Mr. Harikrishna KV. He is the team leader grid planning with CSTEP. Very warm welcome, Harikrishna. Thank you so much for joining us. And we will have Shivani Sharma joining us. She is the principal technical consultant, Hitachi Energy. She'll be joining us virtually. Unfortunately, she's not able to make it at the last minute, but she's agreed to join us virtually. And also, I would like to welcome my colleague Anand, who's the senior manager with India Smart Grid Forum, and he will be making a presentation on the recommendations and the results from the study that ISGF had conducted for Bangalore City. But before that, let me hand over the stage to our moderator, Dr. Tongia. Over to you, sir.
Okay, thank you. Thank you, Reena. And I know the sessions after the lunch are always a little challenging. We've had biomass energy instead of the other energy forms we're discussing here. But I think this is a very key topic, and it's good to have people joining us who have deep domain analysis of the system, because we did a study at my institute 2017, and shameless plug for your own work when it's free. So as a non-profit think tank, all our studies are on our website, Center for Social and Economic Progress, then known as Brookings India. And in this study on EVs, we found that the energy requirement, kWh, from very widespread EVs by 2030, 100% of sales, two-wheeler, three-wheeler, four-wheeler, and buses intra-city, within city, if they get to EV by 2030, so that you have 10% every year growing from 2020 till 2030, the energy impact on the grid is only about 4% of demand, 5%. Very modest. But compared to the energy impact, the KW impact, the capacity of the instantaneous, can be a much greater issue, especially upon the discom. So we presented a hypothetical extreme bounding condition. The best case scenario, let's start with the worst case. Every EV plugs in at the same time, let's say evening, grid peak, 7 p.m., 8 p.m., simultaneously. The best case scenario is you spread out the duty cycle based charging so that you can run your tanki, your tank, 100 kilometers, 200 or 300 or whatever it is, and you charge it in a theoretically perfect way. The ratio between, or the difference from best to worst case, was not 50%. It was 50 times, 50x in difference. So that emphasizes this issue that this is a KW problem and a capacity problem. It is not a KWH problem in aggregate. Second layer to that is it's a very local problem. Transmission in India is generally in good shape. Distribution is reasonably strong in many pockets, but it needs upgrading as soon as we talk about the sizes we're discussing. On one hand, we're seeing that the charging capacities or capabilities of chemistry of batteries and hardware is increasing. 5 years from now, when cars are more mainstream, EV, they will not just be capable of 2, 3, 5, or even 10 kW. It will be not just 50, but potentially 150 kW potential charging capability. That will have enormous impact. And it's good that we have a session with RWAs, for example, because apartment complexes are very interesting. My own complex where I've been on the society, 400 flats. Now imagine there are 400 EVs, each of them trickle slow charging, quote unquote, at 3 kilowatts. That's still 1.2 megawatts just from one vehicle per flat. And in many cases with larger families, 2 people working, it may be more than one vehicle. And if you do a slow charging, then you will need to charge more regularly. Maybe overnight, every night, or at least part of night. So this local aspect is very key. Then you've got the locational impact. Where are these charging stations being set up? It's not as if you set them up everywhere across Bescom, Bengaluru equally. So these are very key aspects. So to kick us off, we have a presentation, I believe it's online, and Mr. Anand will be presenting. Yes. So he's a senior manager with ISGF and has led a number of studies, including with Bescom, on the charging infrastructure requirement. So request him to share the insights in a summarized version of about 15 minutes, if possible. Do we have him online?
I'm audible?
Yes, you are.
Yeah, thank you, Dr. Tongia. I'll just share my screen.
The screen is also visible.
Okay, thank you. Welcome to session 8, EV charging impact on distribution grid. most of previous speakers would have talked about different aspects of EV, and then I'm sure everyone would have a glimpse of the battery technology and several other things. So before starting, I would like to run a short video of 30-40 seconds just to give a glimpse of how it evolved. I'm just sharing my screen.
We could see your screen before.
I have to play this video, so I think, yes. Yeah.
This is the first fully electric taxi from 1943 in Spain. And this is not a gas station. This is a battery quick swap station. When the taxi ran low on battery, they were able to exchange those batteries within 5 minutes. A new full battery gets put in and the taxi can drive around customers again. The old battery, of course, gets recharged and put into the next taxi for the next quick swap. And all this was happening already in 1943.
Thank you for yes. So now it's like it's not very new. 80 years back, almost 80 years back, we had it in Europe, and it evolved in early 1900s. We had it, and then it did not shoot up just because of several reasons. Maybe battery technology is one of the biggest reasons. That is why it did not shoot up early. And then recently we had hybrid electric vehicles around 1997. And then after that, plug-in hybrid electric vehicles we started seeing around 2000. And then after 2010, it came into attraction and focus. People started talking about EVs and started seeing EVs on roads, started using it, or importantly, they started we started seeing regular cars, like not small cars like Reva, Mahindra Reva, and it's like very regular car. So after that, I think after 2010, it was into one of the most shouted thing. So battery technology required DC power. Mostly we give from AC power that is coming from the grid, and then we have a converter, AC to DC converter, and then we give it.
Anand,
Yeah.
we're having a small technical issue because we have 2 or 3 separate streams, including online and live and recorded and stream. If you could slightly slow down your words to have more gap between syllables, because there's a little bit of delay or echo that's catching in. So, I mean, not too much, but if you could just slow it down just a hair,
Okay.
that may make the audio improve a little bit. Thank you.
I can maybe I can switch off my screen if that serves the purpose, and then
No, it's not a
just let
bandwidth
me know.
issue. Yeah,
Uh-huh.
this is fine. Yeah, please continue, but it's not a bandwidth issue. It's an
Okay.
audio feedback issue.
So basically, batteries are they require DC power. Whether you give it from directly to the grid, that where we convert AC to DC, and then there is onboard charges lying on the EV, and then we feed it, and the battery is being charged. And another way is to charge it from DC, that is connected to the grid, and then AC to DC, and then directly DC is supplied to the EV batteries that is lying on the cars. So charging speed depends upon a couple of things. Battery chemistry is one of the most critical thing, where nowadays we are talking about, and there is C rating, through which that decides that how quickly you can charge. It's the technology of the battery, and through which we know that how quickly we can charge the battery. DC power output, onboard charging, AC-DC converters, and DC power output in DC charger. That also is a deciding factor in charging speed, and ambient temperature is also one important thing that plays a role in DC charging. So now coming back to the grid. how electric vehicles are impacting the grid. Every EVs are usually plugged into low voltage distribution, low voltage side of the distribution grid, and there is a huge impact. If it is like a couple of numbers, then it's like additional source of it's like any other additional appliance that is connected to the grid. This can be your geyser or any appliance that is around 2 to 3 kilowatt of drawing energy, 2 to 3 kilowatt. But if it is like huge in numbers, bigger in size, maybe the batteries are the chargers are 9 kilowatt, 10 kilowatt, 15 kilowatt, 25 kilowatt, 50 kilowatt, then this is going to make a huge impact on the grid. Since EV buying behavior is generally dependent upon, generally influenced by the friend or neighborhood, so it's most likely that it is going to form a cluster or a concentration or locality where you get to see most of the EV, those are concentrated. Typically in developing countries, the distribution grid is overloaded during peak hours. So installation of EV charging station require proper planning with data and loading on distribution grid during the day and load flow study. So we did a study in Viscom in 2019 that I'll talk about. And the cost of distribution grid upgrade to accommodate EV charging station may place could be several times more than the cost of EV charging. So that is one of the biggest, most of the critical factor whether we need to upgrade the EV charging infrastructure, the entire grid infrastructure, or we can manage with the available infrastructure by playing with the demand side management or demand response, wherein during off-peak hours we can charge our EVs, and during peak hours we should avoid charging our EV from the grid. So this is mostly from the angle of demand response. Impact on EV on the distribution feeders, mostly when we are charging EVs. So in several studies, it has been seen that you don't have to install a power plant to charge your EVs. There is generation advocacy there, and you can just by playing with the demand and peak and off-peak hours, scheduling your charging time, or during off-peak hours, if you are charging, then this can be managed for a longer time. After that, certainly, once there is like huge number of EVs are into the grid, then you certainly need infrastructure augmentation. And load of in large scale EV deployment in distribution systems, like causing issues, increased demand, increased system losses, and then voltage drop. So these are the issues what we are going to face when there are lots of EVs coming to the grid. And there is another issue, that is power quality, low voltage, under voltage, and then overloading of current. These are few power quality indicators what we may encounter down the line. We took up EV study in 2019 in Bescom itself. So where we tried modeling 12 number of feeders who are having charging stations located on those feeders. So we conducted a load flow study, and then we kind of assumed there was an assumption that we are studying with. There are a couple of scenarios that if there is nothing, then how grid is behaving, and then in 2 years down the line, 2022, then how this is going to behave, and then after 5 years down the line, how grid is going to behave if EVs are maybe progressing, or the growth rate is 6% per annum. So the feeders scenario, most of the feeders, we took 12 feeders, and most of the feeders were found overloaded and struggling with multiple under voltage scenario in the beginning of the study. It's like we did not consider EV then, and in current condition they were facing issues. And EVCS integration on, there is one very important feeder from the perspective of a study, Itamandu feeder, where we found that we need to augment the existing DT from the 63 kVA to 100 kVA, and there are several other recommendations also. I'll discuss it later. And we assume that the load is 80%. 80% load is there, and there were recommendations about how we are going to arrest the harmonics that is being generated on the feeder because of the EV charging station coming into the place, and what is the mitigation of several other issues that we are facing. So we took 12 feeders. All of them were 11 kV single line, 11 kV feeders. So we had the single line diagram, and then peak load. We wanted to understand that what is the peak on the feeder every month, and then current carrying capacity of the feeder. These are several parameters what we took into the account while studying the entire thing. Conductor cable characteristic, rating of distribution transformers, capacity and voltage ratios, EV charging station details, that what is the capacity of EV charging, and then GIS coordinates just to locate that where the station is. And then we also integrated solar rooftop photovoltaic system, assuming that this will also penetrate more in coming years. And the modeling studies were carried out using SignBist. It's a platform software tool through which we modeled the entire thing. So these are the 12 feeders. I'll quickly, yeah, 12 feeders from BESCOM, and then we had how much space every charging station is having there, locality in the city, what is the substation, then the feeder name, the GIS coordinates of the feeder, and the existing capacity of the feeder, charging capacity of every charging station, and then cable size and all. So these are the parameters. Yeah. So the assumption was that 15 kilowatt DC 001 GB by T, 25 kilowatt CCS and Shadmom, 50 kilowatt DC fast charging and 100 kilowatt charger have been assumed by 95%. Other output DC voltages, 15 kilowatt DC charger, 25 kilowatt DC fast charger, 50 kilowatt DC fast charger, 100 kilowatt charger have been taken as 72 volt and 500 volt respectively. So it is assumed that the harmonic injection by solar rooftop photovoltaic system is balanced. We assume that this is the ideal case. This may not be the correct when actually we are putting everything once into the grid. And the consumer load has been divided into the ratio of DT to the sanction load in kilowatt. So we didn't have the actual load per consumer. So we had that how much DT is loaded and then number of consumers we had. So we just divided into a ratio so that we understand that how much individual consumer is impacting. The actual number can be different. The power factor for this Itamandi feeder was assumed 90%. And the efficiency of solar rooftop photovoltaic inverters were 98.4%. And the harmonic injection spectrum for EBCS has been assumed to be the same as the harmonics. So they already had measured the harmonic around their office. So we had that detail available. So we considered this as standard for our research and study. So we divided the entire study into cases. The first case was for 11 kV feeder without EVES, there is no charging station and there is no rooftop solar available. It's like plain and simple. What existed, we studied existing, what is the current situation. And then the second case was we put 44 kilowatt of EVAC load, and then the third case was on the same feeder we assume that 6% growth per year. Per year there is 6% growth, and the EVAC load was 144 kilowatt, and there is a solar rooftop coming in 100 kilowatt, And the fourth case was the same 11 kV feeder, 6% per annum growth. And now this 144 kilo becomes 345 kilowatt, and the EVAC load has grown up to 500 kilowatt. So these were the basic assumptions that this is how in next 5 years the grid is going to behave like. And these are the 12 feeders what we worked upon, and then the parameters were the feeder and the length of the feeder mostly is like 10 kilometers, 4 kilometers, 13 kilometers. How much of them were underground, the total length of the feeder, number of DTs, those are sitting onto individual feeder, then what was the peak load of the feeder, and then what was the EVAC load. So generally we consider it in 2020. There are three scenarios, like in 2020, in 2022, and then 2025. So first year we considered it 44 kilowatt, second year we considered it 144 kilowatt, and third year it was 344 kilowatt. Similarly for solar rooftops also it was 100 kilowatt and then 500 kilowatt in 2025. So I would want to draw your attention. This is very important slide wherein we see that how the existing condition is and how this is going to look like after 5 years. In current situation, we understood that after analyzing the entire thing, we understood that there are a couple of pockets or a couple of sections where we had problem of under voltage and overloading of current. And 5 years down the line, when you see the right side of this picture, this is the situation. This would look like this after 5 years. And if we do not have proper planning of what is happening inside my grid, and that study can be static or dynamic as well, that will give you a better accuracy. But if you do not have it in place, then after 5 years, it is going to be very difficult to control your network you are working with. It's like everywhere there is a problem under voltage overload. So that is why this study becomes more critical. Most of them were not knowing that where the problem is currently, and there is a current problem we are unaware of, and then going ahead it is going to increase only. So I'll just discuss one case, and it was Itamandu feeder. 11 kVA feeder, and these are like three scenarios: 2020, 2022, 2025 loads I have discussed. So we found that there are under voltage locations, 53 locations in 2020. This is going to increase, being going to be 58 in 2022, and after 5 years this is going to be 64. Overload locations were 727. After 2 years this is going to be 793, and then after three more years this is going to be 927. So this is like huge increase in those fault scenarios. And there are and then the mitigation recommendation was to replace existing transformers and to maybe add new transformer to all the feeders or all the sections where we encountered such fault scenarios. So there are a couple of suggestions, like every year or maybe every scenario there was a recommendation of adding new DTs at several locations. And I'll just iterate one. It's Ganpati temple here. It is recommended that you have to have 1000 kVA of one new DT. Then again at some other place it is 100 kVA, 150 kVA, 50 kVA. Similarly, it's like in every condition there is a recommendation that you have to come up, you have to augment your infrastructure, otherwise this is going to be very difficult. The current infrastructure would not be able to sustain. In terms of harmonic mitigations, there were suggestions that C-type filters or harmonic arresters you can put there to avoid the harmonics at several location, and we had 2-3 charging stations at one feeder. So accordingly it was recommended that somewhere it is required 30 kVR of at one place, and another place it was like 150 kVR for 2022 scenario, and similar cases with 2025 scenario. And cable upgrade was required every time. So these are the basic challenges where challenges and solutions as well. I'll talk about that. You have to uh, improve your infrastructure, or you have to add new infrastructure, and to all the feeders. Integration on Itamandu feeder, DT augmentation we discussed, and then there are several other feeders: Hull, ITI, AUX, KIA, DB, C section, Bhatia, Cross RMU, BSK, HSR, EVCS transformer capacity was found sufficient. So couple of feeders there were transformer capacity headrooms available. We could work couple of more years with the existing infrastructure, but there were several feeders where they are struggling now. So you have to look into it and see that whether how we are going to augment the infrastructure. The electric demand of EV charging stations can be served with additional local SRTPV, and there was a different plan through which government is trying to encourage solar rooftop initiative that did not pick up as per the expectation of the government. So I hope in coming 2, 3, 4, 5 years this will pick up. And one of the best advantage from SRTPV was, like, we saw a rise in voltage generation helped to reduce the voltage drop, especially when connected to the tail end of the feeder. So it's like generally we see a drop in every section, and then it keeps dropping, and at the end of the feeder the voltage level is least. But we arrange SRTPV or placed into the system in such a way that if you put it at the end of the feeder, then the voltage level is going to increase, and that will give a better impact on the entire infrastructure rather than putting it. So that can be also planned. It mostly does not depend upon how you're going to plan it. It will depend upon how customers are coming up and they're trying to get into the grid. But obviously this can be kept in mind while planning the entire infrastructure. And the highest current amplitude were observed majority of odd frequency. It was like third, fourth, fifth, seventh, 11th order, and the total distribution destruction was like at the order of 22%, and that is beyond the limit of IEEE 519. LT side we found problem, but in HT side it was 6%, and that was like well within our acceptable limits. And the recommendation, we came up with a couple of recommendations that I'll just go through. Thought leadership on charging use cases, including needs, applications, proper valuation, testing, and validation. So I think DESCOMs have the biggest role to play here when you are planning to include EV as a regular business, and this is going to be an additional customer type, and only planning can save. Otherwise this is very much going to be like the fuel station, where we do not know how many vehicles are coming to my fuel station, and they'll just take fuel and go away. So similar case is going to be faced by the charging stations, where the assumption on load is like, it's very difficult to predict that how many vehicles are going to hit my charging station, and how fastly or slowly they are going to charge, and what impact this is going to give on the grid. So participating in charging communication standards development process, there are several standard committees. ETD 51 is one of them, and there are several others. So the DESCOMs have to play a bigger role, whether if they participate. So they are the real field players who understand that what kind of infrastructure is really required there, and they have their role to play in this standard developments, and then collaboration with industry to adopt best practices. Other was providing EV education and awareness. This program is itself one of the biggest step, I would say, in terms of EV awareness and then reaching out to the consumers and talking about several aspects of EV. And that is well done by Westcom, and several other utilities can also have their own planning like this, whether they can reach to the end consumers, include everyone, and then talk about that how we can solve this bigger problem that we are seeing right now, or mostly we are going to face it down the line, maybe for 5-10 years. Incorporate best practices defined by EV charging infrastructure initiative led by the utility. The area of planning, customer engagement, appraisal, design and development, and customer and regulatory follow-ups are covered by these best practices. Incorporate best practices identified by third-party EV charging infrastructure projects that can be also learned from third parties, and the best practices, there are best practices available, standard best practices available, but that can be altered according to the need of the discom, or maybe in our Indian conditions. And the service and process enhancement can use EV to help low income and unserved segment of consumers, where we can take them on board. So for small consumers, nothing to be worried upon for a couple of years. But for consumers who are going to use charging facility that is more than 15-25 kilowatt, obviously we have to have a proper planning. Otherwise, year on year, this is going to be very difficult, and people are bound to lose control on the network, because if they don't understand it, then controlling it is going to be very difficult year on year. I think I am done for the presentation. If there is any question, we can take it up now, or maybe again when there is an open session for the questions.
Thank you, Anand. No, some questions are there, but we'll save it for a discussion towards the end of it. But thank you for the presentation. My only other observation is, I hope it doesn't take this level of planning per feeder to actually add EV charging stations. Because yesterday we heard that it takes 90 days to get the permission set up. Then otherwise, yeah, or 9 weeks.
There are different places. I think the biggest role in the entire setup will be played by the discoms, because they are the real owners of the entire thing. Logically, this can be owned by anybody else, but they should understand that whether how my grid is going to behave, and they need to plan it properly, or they have to find a way to plan it properly year on year.
So I think the key takeaway is discoms are doing planning based on consumer growth, but this is a new beast that they have to incorporate into their planning system. So
we didn't understand it as a new consumer type, but now EV is a new consumer type. What we have to learn to adopt them in our system. And for smaller consumers, for residential consumers, this is like another additional load. But for bigger consumers, I mean to say, who are having 15 kilowatts or above load on the grid, or they can put this much load on the grid at once, then this is going to be difficult in terms of every DT we have. And I would discuss a very interesting scenario. This is just an assumption, but this is very likely to be possible. Generally, we have an off-peak hour during our 11 o'clock in the night to 5 o'clock in the morning. And suppose people living in posh societies where everybody has planned to switch to EV, and then they really switch to EV in 2 years' time. They're like very pro to green mobility, and everybody buys electric car, and then they start charging during night. They want to charge because the vehicles are at your home during night only, and that is off-peak hour. So certainly you are going to charge it after 11 till 5 o'clock in the morning when the tariff is least. But for that distribution transformer, this is going to be a peak time. This would consume the entire load differently. This is going to be overloaded during off-peak hours. So now the entire dynamics is going to change. So earlier we started doing this from substation, that how much load is on the feeder and how we are going to distribute it, and then the voltage level and the current level. But now this is the time where we have to start thinking on the distribution level, on the DT level, that this DT is going to serve how much EV consumers. So that should be the level of planning going ahead. Or maybe in terms of the phase imbalance also, we have to be very careful, like on 3 phases, if we are putting one charging load on one phase, then it should be balanced. So next load would be on second phase and then third phase. So that should also be kept in mind while giving, if there is like single phase consumers, then this is fine. Then also this needs to be taken care of. But 3 phase consumers, yes, because they would have their own load, and then your additional load you are putting into the grid. So I think planning from my side, this is going to be very critical.
Thank you. I think that's a very good one word to take away is the need for planning and with a new entity like EVs. We'll come back with more discussion very shortly. Any follow-up? I would like to now turn to Mr. Harikrishna, who's a lead at the Center for Study of Science, Technology and Policy, CSEP. Please, can we load up? Does it have to run from there, or can it run from? So just see next slide. If you could give them the laptop there, or can somebody take it? Oh, you have the presentation there. Excellent. Oh, for your reference, yes, because turning around always is a challenge. Yeah,
Yeah. Even we did a similar kind of study what ISGF has done for around 11 fields of BESCOM area. I'm from CSTEP. We are basically a think tank where we do a lot of research analysis to come up with proper policies for net zero by 2050 or whatever the targets India has so far. So we did a similar kind of study for one of the Bangalore urban area feeder. How many electric vehicles need connected, and also how many RTPVs, and what is the potential of RTPVs, and how many RTPVs can be connected to the particular feeder in such a way that the feeder will not be loaded, overloaded, or and also not any grid issues will arise because of more EVs. So going forward, so these are like introduction slides. Like as we are aware of, or as we are all aware of it, like India and all the states have come up with their own policies to transitions towards the green energy and also for decarbonization future. So along with the renewables like solar and wind energy, electric vehicles and also RTPVs plays major role towards this transition. So, and because of this unpredictable nature of unpredictable charging pattern of electric vehicles and also the intermittent nature of RTPV generation. So the grid will be having a lot of impact on these two kind of elements. So through the proper policies and proper mechanism of either charging or either generation of power from RTPVs, EV can act as both load as well as source for the grid in such a way that the grid can be easily balanced without having any overloadings. So next, yeah. So there are several studies like how many electric vehicles can be connected or how many electrical vehicles can be come up in a particular state, and also what is the RTPV potential at each and every rooftops and maybe at the urban levels, mostly at the urban levels. Like there are many studies or many reports are available, but not many studies are there on the effect of the integration of electric vehicles and RTPVs on the grid. So that's why we have chosen this kind of particular study. Like what is the importance? This is being very important. How it will affect on the grid, either integration of electric vehicles or the integration of RTPVs. And we have our own CREST tool, like this is the CSTEP rooftop evaluation tool for solar, where we have hired helicopter to capture the high resolution images of entire Bangalore area network. We have covered almost like 1,100 square kilometer of Bangalore area. where we have captured the high resolution images of the buildings, and we have come up with like what is the potential of each and every rooftop across the city. And we also considered the shading analysis, like if there any shading from the neighboring buildings or any shading from the neighboring trees. So we have nullified all those shading effects, and we have come up with a proper planning tool for each and every individual person within the city. So the tool is available, that is again a web-based tool. Anybody can access if they can give their consumer ID. So they will come to know what is the rooftop potential for their building. And also such kind of analysis are very much required for cities like Bengaluru, considering more EVs can be expected in the coming in the near future. So as I mentioned, we have selected one urban feeder having mixed loads of both domestic as well as commercial loads, and we have executed the analysis for the previous slide. Yeah. So where we have considered an urban feeder, where both domestic as well as commercial establishments are there, and we predicted or we projected load for that particular feeder for the year 2025, and we did load flow analysis using ETAP software, and we have come up with our outputs. Next slide, please. So if you see, as per 19th EPS, 19th Electric Power Survey, the projected demand for Bangalore city limits is around 3,599 megawatt. This is being peak demand for Bangalore city limits compared to 3,067 megawatt as as on 2019 and 20. So we can say the CSGR demand projection is around 3.25% for Bangalore city limits. And also, one of the studies conducted by IIT Kanpur, around 40% of the Bangalore city peak demand would be from electric vehicles. So considering these two factors, the projected demand and also the projected electric vehicles for Bangalore city, we did this study. And also, if you see Karnataka solar policy, it says that 100% of electric mobility, especially the auto rickshaws and cab aggregators, and also the corporate fleets will be, all will be from electric vehicles by 2030. Yeah, next slide. So considering all these factors, so we considered one feeder. The methodology is like that. Like we have collected the feeder information. This particular feeder is emanating from Jayanagar 66/11 kV substation, and we have collected all the distribution transformers, their locations and their loading pattern. There are around 52 distribution transformers are there in that particular feeder, and also we have considered the hourly loading of the feeder for that particular day. And we also collected the information like lat length of that particular DTs, where this particular DT is located. And also the projected demand we have estimated as per the 19th TPS projection. And also the RTPV potential has been established, or we have arrived based on our CSTEP CREST tool, as I mentioned. This CREST tool is available in the web platform. Like anybody can access the CREST tool, and they can get to know what is their building rooftop potential for RTPVs. So we have modeled entire this feeder. We have shown a snapshot of around 5 DTs or 5 to 6 DTs here, but otherwise we have modeled all the 52 DTs for this analysis. And we did power flow analysis. At first, we have benchmarked the analysis based on the existing loading pattern of the feeder. That means either loads at DTs or the loading of the entire feeder have been verified and weighted based on the real-time power flows for that particular instant. And we also this load has been this load has been enhanced for 2025, and also the EVs and the RTPVs have been considered for 2025 scenarios that we will see in the next coming slide. Next slide, please. So this is our CREST tool, and we also mapped. The first one is GIS mapping. We have mapped entire these feeder DTs in that particular area. You can see the geographical map. The icons present in that first snapshot is the DTs. Almost like all the 52 DTs are there. Again, this tool is available in the public domain. If anybody is required, I can share the link with them. So, and the second is the crest tool, where we have shown one building, how many rooftops can be placed, what is the roof potential for the RTPVs, and this will give very elaborative details like what is the technical effect, like what is the commercial analysis, like what is the payback period if they go for RTPVs. All these details can be found in the crest tool. Next slide, please. So for this particular feeder, we have carried out around 5 scenarios. The first scenario is base case scenario. There we have given the existing loading of the DTs, and also we have weighted this feeder like whether the loading we have considered properly for the particular instant. So this is basically for validation purpose. We have considered the existing values for 2019. And the rest all are we have carried out the studies for 2025. So for the second scenario is like business as usual load we have considered for 2025. Here we have not considered any other loads. Like we have not considered any EV loads, or we have not considered any RTPVs for this particular scenario. But otherwise, scenario 3, 4, and 5 are basically we have considered. In the scenario 3, we have considered how many. We have analyzed like how many electric vehicles can be connected to that particular feeder based on the availability of the feeder loading. But otherwise, the scenario 4 is how many RTPVs can be, what is the potential of RTPVs across that feeder, and how much electric vehicles can be connected. If both RTPVs and electric vehicles are there, so what is the capacity of the load, or how many electric vehicles can be connected if you connect RTPVs into that feeder. The fifth one is the difference between fourth and fifth is the RTPV potential have been considered in the fourth scenario is that the RTPV potential is considered assuming that the RTPV can be connected up to 90% of the DT peak load. That means if a particular DT is loaded 80 kilowatt, the 90% of 80 kilowatt, that means 72 kilowatt of RTPV can be connected to that particular DT. But in the fifth scenario, as per the BESCAM guidelines, so we have assumed that the RTPV potential can be connected, or we have connected 80% of the DT capacity in terms of kVA. So let us see the results from all these scenarios. In the first scenario itself, we found that, this is the existing case. One DT is critically loaded. The existing load is around 3.9 megawatt. But in the second scenario, the first scenario is for 2019. The second scenario we did for 2025, where we have considered the CAGR of like the demand growth of around 3.25%. With that, if the same projections, the feeder is loaded up to 68% of its rated capacity, and the available capacity, the rest of the feeder is available for up to 2.16 megawatt. That means up to 2.16 megawatt of electric vehicles loads can be connected to that particular feeder. But in the third scenario, so again in the third scenario we did 2 more scenarios. One is what happens to the feeder loading during the peak instant. That means the peak organic load instant and the off-peak organic load instant. In the peak instant, the 4.6 megawatt remains same. That is the peak instant, the peak load for that particular feeder in 2025. So additional feeder capacity availability is 2.1 megawatt. But in the off-peak instant, the additional load, the additional feeder capacity available is 4.2 megawatt. That means
you're assuming the feeder is 6.7.
Yeah, we assume that like cable. The feeder.
Which conductor did you assume?
That is XLPE 400 square mm XLPE. 6.7 megawatt capacity have assumed.
Because that's not necessarily true everywhere.
Yes. That is it. So again in that feeder, when we go foreign, at some places we saw the overhead lines. Not all the feeder is cable. That is also there. Some places cables will be there from the substation. But when we go far away, the foreign places they might have having still the overhead lines will be there. So that things needs to be taken care. And in the again the scenario 3, During off-peak instant, the off-peak instant usually occurs in the morning time, like around 4 or 4 a.m. But the peak instant, as per our analysis, it has happened in the 19th, that means 7 p.m. So in the off-peak instant, around 7 at 5 electric vehicles can be connected to this particular feeder. But however, in the peak instant, only 380 electric vehicles can be connected. But again, there are 3 DTs are overloaded during peak instant in the scenario 3 itself. And again, during off-peak solar instant, off-peak instant also, the feeder is critically loaded towards 100% of its rated capacity. But when we see scenario 4 and scenario 5, when we inject or when we install RTPV to that system, the RTP potential of 4.1 megawatt has been considered for scenario 4, and the RTP potential of 9.6 megawatt has been considered for scenario 5. In that case, we can go for even around 7 at 5 electric vehicles in scenario 4, and also in scenario 4, in scenario 5 we can go beyond 7 at 5 electric vehicles. The overall summary of this analysis is that, like, if we can connect electric vehicles at a proper instant, or if there is any separate tariff mechanism for electric vehicles, either in terms of incentives, like if government can come up with so and so policies, so and so tariffs, if the electric vehicles can be connected in the either in the early morning hours, some incentives will be given to the consumers, or the tariffs will be very low if they can connect in the early morning hour, something like that. We can utilize the help of existing feeder itself, we can charge more electric vehicles. In the other way, if we can go with RTPVs, more RTPVs, still, there is the possibility, again, if the state can come up with certain policies, during the daytime, when more RTPVs are there, more RTPV generation is there, at that time, more electric vehicles can be connected. Again, if the state can come up with such kind of policies where, from particular duration, like, morning 11 o'clock to either morning 11 to afternoon 3 o'clock or 4 o'clock, some incentives will be there, or some subsidies will be there for electric vehicle charging. Again, in this case, more electric vehicles can be charged during those time instants. But otherwise, if we don't come up with the proper mechanism, proper policies, if all the electric vehicles are charged in the evening time, then the city demand is very high. So obviously, we will come up with this kind of issues, overloading of network elements or overloading of DTs. All these things will be come up in the near future. Next slide, please. Yeah, so this is as part of another study. We did one more study for again Bangalore city itself, since it is more relevant to this forum. That's why I bought this. I'm trying to show this slide, but otherwise this is more relevant to another study altogether. So again, we did a similar kind of study for Bangalore city. We have explored, like, we have projected the how many electric vehicles will be there by 26-27, especially for Bangalore city. This number of electric vehicles and all, again, we have referred various transport department reports where we have aggregated past 4 to 5 years of data, where we come to know that, like, by 2020, these are, like, if you see 2020 column, these many electric vehicles, two-wheelers, these many four-wheelers, this is like around 95 lakhs 54,000 of total vehicles will be there in Bangalore city by 2020. And if we can project this with the same year for 2027, the number of vehicles in Bangalore city will be around 1 crore 57 lakhs 78,000 number of, these are like number of total vehicles. And as per government policies, the policy says that by 2030, all the two-wheelers will be electrified, all the three-wheelers will be electrified, something like that. But if we consider at least 30% of electric and 30% of two-wheelers will be electrified by 2027, then the number will be coming up like 32 lakhs two-wheelers, and the four-wheelers are like 5 lakhs, and the three-wheelers are like 3 lakhs 79,000. And of course, various government is coming up with to buying 1,500 buses for city limits. Altogether, we will come to a number of like 42 lakhs of electric vehicles can be seen by Bangalore city alone. around 42 lakhs of electric vehicles will be there in Bangalore city alone. That we have considered only 30%, 20% on that. But if you see for 2030, in that case, all the two-wheelers are electrified. That means we will go beyond 1 crore and all. So with this 42 lakhs electric vehicles itself, the peak demand Bangalore city will be experiencing around 1984 megawatt. Assume that the current load of Bangalore is around 3000 megawatt, 2000 something or 3000 something, 3000 megawatts, I guess, the current city load. So if almost like this is like 60 to 70% of the existing load. If the peak demand of electric vehicles comes up in the same peak demand of Bangalore city load, then imagine how much extra infrastructure is required for Bangalore city. Yes, yes, sir.
Hypothesis set for this study from 2019 to 2000. You are now stating that the peak demand which is 1984 megawatt
Yes, yes, yes.
in Bangalore city, only in PV.
Yes,
Want to know what is the hypothesis set you for your study?
yes, yes, yeah. So,
The electric vehicle supply system remains the same constant for the next 5 years. The demand remains the same for next 5 years. The charging capacity. The capacity of AC charging and DC charging remains same for next 5 years. Is it like that?
so yeah, we are not trying to.
There will be an incremental implementation in all. If such is the case, is it true that 2000 megawatt? Because we are not. Our director technical is also addressing the staff. All our chief engineers are addressing here. All our senior officers. On behalf of them, I am asking. Just not the hypothesis.
So the hypothesis for this is like number of electric vehicles. But see, as per Karnataka EV policy, the policy states that by 2030, all two-wheelers are going to be EVs. All
So just
auto
to
rickshaws.
clarify, that is all sales will be EV,
Sales.
not
Okay,
the fleet, because the old ones will remain. Yeah,
The new certain techniques and other things exist. The policy. I don't know any changes in the policy, but we have considered as per the policy. You are right, sir. We have not considered any technological advancement going to be. I mean, from now, another 5 years, anything can happen.
Those things we are not aware of it, and we have not considered those technological advancements. We have considered.
We agree, sir.
Okay.
But you please consider that also and
Okay.
make a
Got it. Yes, I agree. But this is like worst case scenario.
Anything can happen below this also.
Any other road reducers are remain would say automatically the growth is high. Some contracting
No, see, as per organic growth, they have considered as per 19 TPS projections. So they have again come up with their own projections for all the metro cities, including Bangalore city. He has done studies for Bengaluru, Mumbai, such kind of other cities. Okay. Yeah, so yeah, I agree. CA has not considered any electric vehicles in their projections. Yes. Yes, this is additional load. No. The 3% is there for Bangalore from long time. So, yes. Exists. If we go as per the policies. Pardon? Okay. Can you give mic for them?
So, sir, if we could just hold off the question for 2 minutes, let him finish his presentation. It may be, if you
Yes.
could come to the conclusion quickly.
I think this is last step. So yes, yeah. Yeah, we can discuss later. So yeah, as per our analysis, the Bangalore, again with this many electric vehicles, the CO2 reductions will be around 2,33,858 tons. If we can go with this proposal by 26-27 itself, we can reduce around more than 2,33,000 tons of CO2 emissions into the atmosphere. So on this pattern has been taken from the EV charging profile has been taken from some of the Europe countries reports, because we don't have any, at least in India, we don't have any such kind of pattern analysis. No such kind of reports are available so far. So we have assumed, like we have read some McKinsey report. We assumed that all the electric vehicles are the charging of electric vehicles will be more in the night time, especially either 11 to 12. It will reach its peak charging time. So that's how we have come up with this, the expected demand for Bangalore city is around 1,984 megawatt. Yeah, next slide, please. So the key recommendations or key takeaways from this study is that feeder-wise analysis is very much required for all the feeders within the Bangalore city. If not, at least all the feeders, at least category-wise feeders. Domestic feeders, few domestic feeders, few commercial feeders, few industrial feeders, mixed feeders, domestic plus commercial plus industries, or if there are any other categories which BESCOM might be knowing very well, such kind of analysis is to be carried out, because the number of feeders in Bengaluru, I guess more than 1,000 feeders. So it will be very difficult to do analysis for all the 1,000 feeders. At least category wise, if we can segregate and if we can do proper analysis, at least 50 to 60 feeders, that will help even the utility to plan properly, and they will come to know how much they need to upgrade their network and how many electric vehicles can be expected within Bangalore city, all those aspects. And one more suggestion is along with EVs, it is also better to go with RTPVs because you no need to duplicate or double the infrastructure. With the help of RTPVs, some of the EV, some of the upgradations can be postponed, or some of the upgradations, network upgradations can be reduced. So and daytime EV charging is always recommended with RTPV connections into it. And of course, a better load forecasting is always recommended because for all these electric vehicles and RTPVs, if we have proper load forecasting, it always helps only, both utilities and also the consumer level. So yeah, that's it. Thanks from my side.
Thank you. So maybe you can join me back and then we can have discussion, because already number of questions were flagged. I'll bring together a few of the points that were raised. One observation in your slide 10, where you showed the EV charging curve, it almost looked like a mirror of what the solar would do. And that's a problem, because your EV charging curve was evening heavy, so-called grid low. So this is one issue that will need reconciliation from both public awareness, I think. So right now, EV pricing does not have any COD aspect. So consumers will at some point need to be incentivized to match the RE and the solar especially, because wind is more seasonal. And now coming to the general issue on the distribution infrastructure and DISCOM side, sir, you had a question. If we could request a mic.
This technology, battery electric storage system. 1 megawatt, you only 20 to 30 minutes. So you're asking about storage technology to synergize with battery, with solar, rooftop. So the issue is there.
Ultimately one of economics and pricing signals. Is the end consumer with the rooftop supposed to put the battery, or is the DISCOM supposed to put the battery to smoothen out the supply vis-a-vis the demand, which may be EV or non-EV? These are the issues that will have to be reconciled. On a pure energy basis, yes, the shape of that curve, you could help it match with storage, but at what cost? Because now you're doing double storage. So the catch is, I mean, this is a longer discussion on storage. As of now, storage costs are still a premium. Sorry? So over time, yes, that state-of-the-art technology will improve and it will become cost-effective. But in the short run, one is the market will decide for itself based on the pricing signals that are available. The second question is at a policy level. So, for example, today EVs are not having any TOD signaling. So if I have no TOD signal as an end consumer, I don't care. No incentive to not charge at 8 p.m., which is the worst time from the grid perspective.
No, right? Hello? 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 Yeah. So here we are thinking about local generation. That means, if you can generate power, am I audible?
Yeah.
If you can generate power in the local distribution grid, transporting power from the faraway places, from solar plants or wind plants or from thermal generations, all this can be negated. There are two advantages here. You can generate, if you can adopt a policy where you can generate power from RTPVs, you can generate and consume then and there only. Instead of transmitting all the, even if you go for battery storage technologies, again you need to transport power from the faraway places.
No. I am requesting you can put it in your own premises building.
He's saying
Best
joint
power you can
associated.
charge
Yeah.
from your best power.
So
you
that
can
gets
charge.
the issue of is it bundled or unbundled and what is the tariff policy associated with that? So that is a separate discussion we'll have to come back to.
No
Your
issue.
point is well taken. It's a very valid suggestion but it's not yet been answered. Your question is correct, but the regulator has not answered that question yet.
But instead of putting RTPV in the government rooftop building, the space is not available for the emergency, any critical disaster, anything. So if you consider the battery electric storage system, it is better.
Yeah. So the where we locate it will also evolve with the who can own it and who can sell or resell. Because electric vehicle has a waiver under Electricity Act that it is not considered reselling. But if I do third party through storage, then that is considered reselling. And as of now, it is not allowed under the Electricity Act. So these are things that will have to evolve. We have with us now Dr. Shivani Sharma. Thank you for joining us. Glad you could make it. I believe you were traveling. So welcome and look forward to some brief remarks. Thank you.
Hi, very good evening. Please do confirm if I'm audible.
Loud and clear.
Oh, okay, great. So I apologize. In fact, I was just traveling and we had a SpiceJet incident today. I guess few of you would have heard it. There was an emergency landing to a flight. Is very important, and even the many discussions that go on the EV safety, which are recently going on. Have just landed. I would just try to quickly touch upon few very important points, and I'm not having a presentation, but however, I was really very delighted to hear the discussions of the previous panelists, and somewhere I feel that I belong to Power Consulting, Hitachi Energy, and we are the fortunate ones in the power consulting who are responsible for the grid integration of these EVs. So initially, there are just very two, three important aspects that we should understand. The first one being the typical characteristic of the EV load. So as somebody was mentioning, it will be charged in the evening. So it's the way we would take it is we always, consider the different profiles, whether it's a residential, commercial, industrial load one. The utilities in India, they are quite old, and till now, the quantum of EV is very limited. But as and when by 2030, 2040, the quantum of this EV load is increasing, the impact on the distribution grid is going to increase. And that's where it's very important, because EV is a very typical load. It is it could be at any point, the time could be anywhere. And at the same time, it's important to understand that what is the demographic and the standard of living of Indian citizens. So say what's going to be the population growth, what's going to be the percentage increase in standard of income, how much people would use cars, majority would use the two-wheelers, in the metros they would use public infrastructure, and so on. So that's where it becomes very important to understand the kind of load, at the same time the kind of charging. So are we talking of slow charging, which could be the typical ones in the residential areas? Are we talking of fast charging, ultra fast charging at the highways, and so on? So that's one from the load part, which is very important. At the same time, it is of utmost importance that we do model our distribution grid. We take into concern the asset health, the present asset health. So there will be society area uh, nearly loaded, completely loaded. How do we identify that what's the kind of load and generation cycle? What is the kind of charging you would see into the system? So that's where the hosting amount of load you are trying to integrate into the system, as well as what is the equivalent PV and the microgrid integration scenarios, the different combinations you could have into the system. So whenever we are going ahead with fleet charging with EV infrastructure, it's very important to consider the time of charging, the type of load, the existing health of the distribution segments. Would you require a new transformer? Would you require, say, a small substation? The electrical design. So overall, I think it's a very interesting grid integration aspect from the power consulting Hitachi Energy that I would like to represent. And whenever we are planning to integrate, a very careful analysis considering the technical, the commercial, as well as the regulatory, the location specific compliance codes becomes very, very important. So that was the brief and the most important points from my end. Thank you.
Thank you. Dr. Sharma. Uh, I think this planning aspect has been touched on, of course, by all our presenters. So I think there is no disagreement. The question now really becomes planning within which constraints and what guidelines, because the regulators and policymakers are the ones who set the signaling for planning. So, for example, the other phrase that's key, I think, for discussion is the time of day aspect. Because when a consumer wishes to charge, what freedom they have. So if I have choice, I'll charge it either when it's cheaper or when it's greener, if it's the same price. But what if neither of these three are aligning? You have three different criteria. And right now that signaling is itself missing. So when a question to BESCOM or to general, maybe it's rhetorical. DISCOMs operate on the aggregate revenue requirement ARR basis. Their costs are set up before the regulator, who may or should approve most of them, and then they are used to set a tariff, and this tariff is set in a manner that balances fairness, social welfare redistribution, and cost recovery to the DISCOM. Now here, there is an element of cross subsidies that has always been part of a development strategy nationally, not just in Karnataka. Now, if we take this hypothetical, you had said 40% EVs, I think that's a little too much realistically. Let's assume in 2025, 6, 7, doesn't matter, few years from now, we're talking just 5% of your consumers putting up a 3 kilowatt charging. So 3 is a small by four-wheeler, easy, but decent by two-wheeler requirement. So putting this rough crude number, one feeder will have 3, 4, 5,000 consumers, depending on feeder, few thousand. Now if 10% switch, and now you are giving 3 kVA to them, that's little over 1 megawatt of additional sizing. Question becomes, is BESCOM planning to socialize all of this? Or is it that the fixed cost for all of the EV should be charged to the EV consumer? Because as of now, today it is socialized. The variable cost is itself lower than ACS average cost of supply. And it is not much higher than the APPC, the average power procurement cost for the DISCOM. So this is a fundamental social question. Today, when the percentage is 1%, it's okay, doesn't matter. But when you hit 5%, 10%, 20%, then 30%, this will become a fundamental question. So the two questions that I'm sort of leaving as closing questions, maybe somebody from our DISCOM leadership, seniors, or anybody could just share some thoughts. One is, how much headroom? You cited one feeder. The ISGF looked at 12 feeders. Question becomes not any specific feeder, but what is the distribution of feeders? How does it look like in residential heavy areas where people will be charging more of their feeders? Because I'm not convinced that they have 2 or 3 megawatts of headroom in existing feeders. Or is it the case that that much headroom is there? If I could request, if anybody is brave enough to share.
So normally, the feeders are loaded up to 60 to 70% of their capacity. So the remaining margin, either at distribution level or transmission level,
but
they
that's
normally keep.
No, that's a heuristic. Let's hear from the actual, what is it spread like across the DISCOM? Because average numbers are misleading.
I have taken the permission from my Honorable Director Technical. Sir, I have listened to the gentleman who is on VC. Here, the electrical distribution network, the redundancy factor factors in redundancy of the 11 kV feeder, redundancy of the distribution transformers, redundancy of the substations. At what level of redundancy the system is in place? Now we are in the power sufficiency era, not in the power deficiency era. Our peak load about 10 years back, it is sinusoidal. Morning peak, again evening peak, 2 peaks, 2 hyperbolas. Now there is no, it is not the case. Now from 2019 onward, from past couple of years, we are in power sufficiency and our load is almost flat. And our generation mix also changed. Earlier only hydro and thermal and a small portion of renewables. Now renewables also account for 40% of my generation mix. Renewable means from morning 7 o'clock to evening 5 o'clock, I have complete sun radiation and I can utilize the renewable energy. That is fed to our agricultural feeders also. During the night time, no issue at all. My night load suffices my morning load because I have already factored in my agriculture load in the morning itself. Now even if any ample number of EV capacities or numbers comes in, my system is already taken into consideration. There is no
disturbance in the, it is not foreseen any disturbance in the distribution network. With respect to distribution transformer, all the distribution transformers are working with the redundancy up to 120%. But whereas BESCOM, consistently we are every year adding our new transformers, and our loading factor also earlier, about 10 years back, is hovering around 90% to 100% fully loaded distribution transformers. Now, no, there is vertical growth in the Bangalore city. All the apartments and all other commercial establishments have the distribution transformers. Each house or each mall, each residential building is having its own distribution transformer. That has created the headroom for redundancy factor. My now loading factor has come down about almost 20%. Now my distribution transformer loading is hovering around 60 to 75%. And if the situation continues with the changes and amendments in the Electricity Act, again we can see number of transformers coming up, and we will definitely incorporate all these EV loads also. Thank you very much.
Thank you. So that gives a lot of breathing room from the technical perspective. Absolutely. Are there any questions from the audience?
Sir, I would just add a very quick point to this, that while we are having aging utilities, while the loading is increasing, we are also having new kind of energy mix that is getting integrated. So a real-time decision making where you would decide that when a solar is available, what is the amount of battery storage I would like to have into the system. There is always a different combination of this energy mix that would go for any.
Madam,
Shivani, your video is off.
Yeah, actually, I just came out of the flight, so I'm at the luggage
You're
belt.
audible. Sorry,
So,
please continue. Yeah.
yeah. So what I was trying to say, that even in case of transformers, in case of conductors, we would like to say that what are those which are critically loaded, what are those which have a marginal capacity available. Again, at the same time, we try to identify what are the bottleneck equipments in that particular distribution network in a priority sequence. So is it some transformer, is it some conductor getting overloaded? Would we like to augment it? Would we like to replace it or have a new infrastructure, and so on? Are the different aspects that we would like to explore for any particular network on a case-to-case basis. So that's where once we have new players at the load, at the generation, again, an important consideration is to place them properly in a proper quantity. And as somebody said correctly, availability for India now is not an issue, but the quality of power, the safety, etc., are the other aspects that we have to work towards. Thank you.
Thank you. I think one last takeaway I have is BESCOM. Yesterday we said to our friend from Delhi that BSES is not all India. Also, BESCOM is not, unfortunately, it's not all India because it is a leading DISCOM. If only the other DISCOMs were taking lessons from BESCOM, I think the country could accelerate its transition. So with that, thank you very much, everyone. Thank you to our panelists. Thank you, Dr. Sharma and Anand.
Okay, I have
Thank you,
one
Aditya.
burning question actually.
Thanks a lot. Thanks a lot for being patient with me.
I have one burning question, last question. This is to BESCOM actually, since DT is here, Director Anand is here. So, I'll just ask question because there is no solution for this. So, I guess as of now, what I heard is like in the remote, like village sites and all, since the EVs are even going to village sites, so what they're doing is like they're charging their electric vehicles in their pump set places, irrigation pump set places, where we are supplying free of cost power to them. Yeah. Okay. No, yeah, I mean they're charging their electric vehicles. No. This is unofficial.
We are official.
So how we adjust, I think, is a different discussion.
How do we account? We are officially stating in rural area also, we have Nirantara Jyoti feeder. Nirantara Jyoti feeders, 24 hours paying feeders. Thank you.
If I could request our Shivani, would it be possible for you to turn on your camera for just a second? We're going to take a group photo and you could join us virtually in case it's technologically feasible.
You can be there next to the screen and Anand is there. Shivani has
think
left,
left.
unfortunately,
Okay,
yeah. You can come closer to the screen, yeah? Yeah, may I request the Director Technical Bestcom sir also to please join on the stage for a picture. All good? Thank you, sir. You've